Okay, so good morning, everyone. Today we will be discussing on our topic one, which is on vectors. So here's the definition of vector. So vector is a quantity that has two independent properties, and these two independent properties are known as the magnitude and the direction. So magnitude is the one that is giving you an idea on how long or how short or how strong the vector is. So, and then direction is giving you on what direction the vector is pointing. So there are two different ways of representing vectors. So we can represent it in terms of graphical representation, and we can also write vectors in terms of mathematical representation. So for the graphical representation, that means that we can write or we can draw the vector in terms of an arrow. So you represent a vector using an arrow, which will always have the tail, so that is where the vector came from, or that is the starting point. And it also have a head, which will be represented or indicated by this arrow head. So the length of this arrow should represent the magnitude or how long or how strong the vector is. And of course, the vector head should always point to the direction of the vector. So say for example, if the vector is going to the positive x-axis, then this arrowhead should be pointing to the positive x-axis. Now, in the mathematical representation, we also have to write the vector in terms of its component. So just like here in the graphical representation. Again, in the graphical representation, we represent the magnitude as to how long this arrow is, and then we represent the direction with this arrowhead. While in the mathematical representation, we just write the vector in terms of magnitude plus we indicate the unit vector, which is giving us the direction. So magnitude, again, it is the number that measures how long the vector is. And the unit vector in the mathematical representation is the one that represents the vector's direction. So the unit vector can be written in terms of the x, y, and z. So it can be positive, negative, x, y, and z axis, just like what you see in the Cartesian coordinate. And we can also represent it in terms of ijk. So ijk is just like the x, y, and z, so do not be confused. And we can also represent the direction in terms of NESW, or the north, east, south, and west. So here are some examples of vectors in physics. Of course, we have the displacement. So in the displacement here, we have an example, 3 meters to the south, which means that 3 meters is the magnitude of the vector and south is its direction. Another example is the velocity. So here we have an example, 4.5 meters per second to the positive y-axis. So 4.5 meters per second is the magnitude of this vector, and y, positive y, is the direction. Another example is, of course, the momentum. So here we have an example, 1 kilogram meters per second to the positive z-axis, which means that 1 kilogram meters per second is the magnitude of this vector, and z, or positive z-axis, is its direction. And another example, of course, is the force. We have here an example of force, 5 newtons, 45 uh, 45 degrees south of east. So 5 newtons is the magnitude of this vector, and 45 degrees south of east is the direction of this vector. So you have to take note as well that if the quantity does not have a direction, that means we call that as scalar quantity. So for example, these are our examples for the vector quantity, right? So if we remove the direction of each of these examples, say for example, we have 3 meters only, we do not have the direction, then 3 meters is called scalar quantity, it is no longer a vector quantity because we remove the direction. But if we have both the magnitude and the direction, we call that a vector quantity. So I hope that is clear. Now, another clarification on the direction. So again, direction gives the information on where the vector is going or where it is pointing. So we can represent it in terms of the x, y, or z axis, as you can see here in our Cartesian coordinate. So this is just a review on what you have learned in your high school in mathematics. So you have the Cartesian coordinate, and we have there 4 quadrants, right? So we have the first quadrant, the second, the third, and the fourth quadrant. And each of this quadrant, we have 90 degrees angle. So this is 90 degrees, this is 90 degrees, this is 90 degrees, and this is 90 degrees. And again, we have another representation of direction. Instead of using x and y axis, we can also use this. So this is our typical directions used in navigation. So we have the east, the west, the north, and the south. And of course, just like here in your Cartesian coordinate, the angle from the east to north is 90 degrees, the north to west is 90 degrees, west to south is 90 degrees, and south to east is another 90 degrees. Now, you have to take note that some vectors lie only along the x-axis or along the y-axis, but some vectors may not lie in any of these axes, but instead lie in between. So in our examples a while ago, here we have to the south, so it is strictly towards the south, no angles that indicate its deviation from the south. Here we have strictly positive y-axis, so it is really going towards the positive y-axis. Another example we have here towards the positive z-axis, so it is really going towards the positive z-axis. But how about the last example, 45 degrees south of east? So therefore, there are some vectors that do not lie in a straight line, say for example, towards this direction only, or towards that direction only, or in the opposite direction, straight line. But rather, there are some vectors that lie in between these axes. In other words, some vectors are located here, some vectors are located here. So in between these axes. So it could be in the first quadrant, in the second quadrant, in the third, or in the fourth. So in those cases where your vector is lying in between axes, so we need to represent the direction of that vector in terms of the reference angle as highlighted here, just like what we do here. So in this case, instead of just saying south of east, we say 45 degrees south of east to specify what is really the direction of this vector since it is lying between the south and the east. So it must be somewhere here, but we indicated its angle as 45 degrees south of east. So that means if this is the navigation, south of east, that means that you go to east and then you measure 45 degrees to facing the south. And so your vector, the last example in the previous slide here, this vector should be somewhere here. So it should be pointing towards that direction. Okay, so I hope that is clear. So reference angle. So let's dig deeper into the reference angle, or what is the definition of this reference angle. So reference angle is a measure from x-axis towards the vector in the counterclockwise motion. So you have to remember this one. So the reference angle should be measured from the positive x-axis. Say for example, in this representation, we have here the positive x, the negative x, the positive y, and the negative y. Always remember that this is the convention, or this is the normal labeling of our Cartesian coordinate. So your x-axis should be going towards the right. The negative x-axis should be towards the left. Positive y is upwards and negative y is downwards. So let's be uniform in using this one. So your reference angle should be measured from the positive x-axis towards the vector in a counterclockwise motion, which means that If this is the vector, then you should measure this reference angle from this positive x-axis towards that direction, not the clockwise direction, but this one. So for this example, your reference angle is this angle. On the other hand, we have another example here. So again, we have the same Cartesian coordinate. We have here the positive x in the right, negative x on the left, positive y in the upper portion, and negative y in the lower portion. We measure the reference angle counterclockwise from the positive x-axis towards the vector. So if this is your vector, then you measure the reference angle from this point towards that direction. So this is our reference angle. So for these examples, in the first example, we have the reference angle equal to 40 degrees, while in our second example, we have the reference angle equal to 240 degrees. Now, again, how do we determine the reference angle if we have vectors given here? So we have two examples, okay? So our first example, we call it vector B. I put an arrow above the B to indicate that this is a vector quantity. So if wala na siya arrow, that means that this is a scalar quantity and we do not have any direction. But if we have here an arrow above the vector name, that means that this quantity have a direction, and that means that this quantity is a vector quantity. So on our example, we have vector B is equal to 5 meters 30 degrees west of north. So how do we measure for the reference angle of this vector? So what we do is that first we draw the Cartesian coordinate, as you can see here, and then we draw this vector. So we have 5 meters. So we draw an arrow. We should represent 5 meters here in our direction. So if you have a ruler, you can represent 5 meters by 5 centimeters, or maybe you can also use 5 inches as long as you have a proper scaling. So here we represent our 5 meters by 5 cm, and then 30 degrees west of north. Um, how do we draw this one? So first you go to north. This is the north, the upper portion of our Cartesian coordinate. This is also called the positive y-axis. And then once we are already in the north, we will measure 30 degrees towards the west. So this is the direction of our vector, and its magnitude is referred to us by the length of this arrow, right? So what is the reference angle of this vector? So this vector is located here. Never mind these component arrows. So just focus on this yellow arrow. So the reference angle of this should be from the positive x-axis towards that direction. Okay, so how do we measure that angle? So we know that in the first quadrant, we have 90 degrees, right? Because from the positive x-axis, this is positive, to the positive y-axis, we have a total of 90 degrees. And since we have here another 30 degrees, all we have to do is to add 90 degrees and 30 degrees, and that should give us the reference angle of 120 degrees. Now, let's go to our second example. For our vector C, we have 5 meters again, but it is located 25 degrees south of west. So how do we find this direction? So first we go to the west. So this is the west, the negative x-axis. And then we face the south, right? Because this is south of west. So we go to west first, and then we face the south. And from that, we measure 25 degrees na angle. So by that, we know that in the first quadrant here, we have 90 degrees. And then in the second quadrant, we have another 90 degrees. That's why we have here 90 plus 90. And then here in the third quadrant, before we reach our vector, we have another 25 degrees. So that means 90 plus 90 plus 25 degrees. And that should give us a reference angle of 205 degrees. So that is how we find the reference angle, and I hope you master this one. So you have to take note again that the reference angle is the angle from the positive x-axis to the vector in the counterclockwise motion or counterclockwise measurement. Other than that, if you measure it in a clockwise motion, then you will get a wrong answer because as you can notice, this amount of angle is different to this angle. So you should really take note that we are measuring the reference angle in counterclockwise motion from the positive x-axis towards the vector itself. So this is towards that direction. So for you to remember that one, you just imagine how the hand of the clock moves. So it is moving in clockwise. So you should measure the angle opposite to that direction. So the clock is moving towards that direction. So that means that since we are measuring the reference angle in the counterclockwise motion, so that means that we are opposing that motion and instead measure the reference angle in that direction towards the left. Okay, so now that you know already what is the reference angle and how we write vectors in terms of graphical method and mathematical representation, let's go to the vectors and their components. Okay, so as you can notice here, we have our vector that is located in between the north and the west, or located between the positive y-axis and negative x-axis. And you can notice here that we have component arrows, right? So this is our vector. But if you break down this vector, you can see that you have here an x component and a y component. So that is the components, those are the components that we are talking about here. So for the vectors, we have x component and y component, especially those vectors that are located in between the axes. So say for example, in those vectors that are strictly towards the positive x or towards the positive y, then these vectors do not have components, right? Because they do not lie in between axes. However, if you have some vector like this one, like our example a while ago, these examples, they are located in between different axes, or they are inside specific quadrants. That means that these types of vectors have components, which are the x and the y component. So how do we look for the x and the y component of the vector? So these are the equations. So first, if you are looking for the x component of vector A, this is our vector A, the magnitude of the vector A, how long or how strong the vector A is, all you have to do is to multiply that magnitude by cosine of theta, where theta is the reference angle. So that should give you the x component of the um, vector A. How about the y component of the same vector A? So all you have to do to find the y component of the vector A is to multiply the magnitude of vector A by sine theta, where theta is the reference angle. So that should give you an idea that again, to find the x component, all you have to do is to multiply the magnitude of that vector by cosine theta. And to find the y component, all you have to do is to multiply again the magnitude by sine theta, where theta here are the reference angle. Again, the reference angle is this one, the angle from the positive x-axis towards the vector in counterclockwise direction. So before we can use vectors to solve problems, we must resolve them into their components. So that's why it is important that you memorize these equations. So don't be confused by this. So phi here, this is another Greek letter to represent angle, but this is still our reference angle, okay? So to calculate for the x component, again, you just multiply the magnitude, or how long this arrow is, the magnitude of this vector, by cosine of the reference angle. Again, for this example, our reference angle is this one. And for the y component, all you have to do is to multiply again the magnitude of this vector by the sine of the reference angle. So in this representation, the x component is just this length, this is the component of this vector that is parallel to the x axis. That's why we call it the x component, while the y component is the component of this vector that is parallel to the y axis. So that's why we have it here represented by this blue arrow. And again, you can calculate it using this equation. And mind you that our vector can be represented by this. So you can represent, this is our vector A. So you can write vector A instead of writing it in this manner. So you can see the magnitude of this vector plus its direction. You can write it in terms of its components. So you can write it just like this. So you write first the x component and then put the direction of x, and then plus the y component and then put the direction of y. And to calculate back the magnitude of vector A, you can always use this equation. So this is from the Pythagorean theorem. So you can calculate for the magnitude of vector A by getting the square root of the square of the x component plus the square of the y component. And to find this reference angle, if you know the y component and you know the x component from these equations, okay, so after you calculate the y component and the x component, you can always calculate for this reference angle if you do not know this reference angle by using this equation. So if you use your scientific calculator, all you have to do is to use this. So this is in absolute value. I have to remind you, this is in absolute value. So the reference angle is just equal to the inverse tangent of the absolute value of the y component divided by the x component. So where are these x component and y component? So in our previous example, remember in our previous slide, these examples here. So in our examples a while ago, so this is the vector. So the x component here is this one. Again, x component is always parallel to the x axis. And the y component is this one, where the y component is always parallel to the y axis. So the same is true for our second example. So this is the vector. This is its y component. Again, as you can notice, it is parallel to the y axis. And this is its x component, which is parallel to the x axis. Okay. So how do we solve for the x and y component of the following vectors? So these are the same examples a while ago. I used these examples again because we were able to calculate already for the reference angle here, right? So in our previous slides, we calculated for the reference angle of this vector, and we calculated also for the reference angle of this vector. So how do we calculate for the x component and the y component of these two vectors? So for the first example, to calculate for the x component of this vector b, all you have to do is to x component of vector b is just equal to the magnitude of this vector b, which is equal to 5 meters, right? So we have here 5 times the cosine of the reference angle. So cosine, our reference angle here is 120 degrees. So you have to evaluate this in degree mode in your calculator. Again, I have to remind you that you have to evaluate this in degree mode in your calculator. So again, 5 meters, this is the magnitude of our vector, times the cosine of our reference angle, which is 120 degrees, and that should give you negative 2.5 meters, which is true because we have here negative value because, as you can see, the x component here is pointing towards the negative x-axis, right? Now, how about the y component? So the equation is magnitude of our vector b times the sine of our reference angle. So our magnitude again is 5 meters. So all we have to do is 5 meters times the sine of 120 degrees na reference angle. And if you evaluate this in your calculator, this should give you 4.33 meters na y component, which is true. This is positive because, as you can see here, the y component is pointing towards the positive y axis. How about our next example? So for this, the same equation, so to calculate for the x component of vector c, all you have to do is to multiply the magnitude of vector c by cosine of the reference angle, which is 205 degrees. So the magnitude of vector c is 5 meters times the cosine of reference angle 205 degrees. This should give you negative 4.53 meters. And again, this is negative because x component here is pointing towards the negative x component. And how about the y component? So to calculate for the y component of vector c, all you have to do is to multiply the magnitude of vector c, which is 5 meters, by the sine of the reference angle, which is 250 degrees. So 5 meters times the sine of 205 degrees will just be equal to negative 2.11 meters, which is negative because, as you can see here, the y component is going towards the negative y axis. So you have to remember again that when doing this, so cosine of theta, theta is not equal to these angles, as you can see. So again, this theta here is the reference angle, not these angles indicated in the given. So you have to be careful with this. So for your assignment, you have to identify if these quantities here are scalar or vector. So you already know the difference between the scalar and the vector quantities. So there are 5 items here. So answer in your notebook. And then another assignment is you have to determine for the reference angle of the x and y components of each of these vectors. So we have here first vector, second, third, fourth, and fifth. So you have 5 items, and you have to look for the reference angle and the x component and the y component of each of these vectors. So write your answers in the notebook, and we will be checking this next week if our classroom is already ready for the class. So that's all for today, and thank you so much.